Hi, this is a pre-lab lecture for the Chem 104 experiment on measuring pH using indicators. The first topic we have to address is what is an acid and what's a base. In one of the most popular definitions, there's a few different definitions. Arrhenius had a definition. Acids produce H plus and bases produce hydroxide OH minus. Brønsted-Lowery is a little bit more versatile. It doesn't depend on the OH minus of a base. Bases are things that accept H pluses. Acids are things that donate H pluses. And an H plus is also called a proton informally because the most common isotope of hydrogen includes one electron and one proton. And when you lose that electron, you get H plus. It's just the proton. So one way to think about, or one helpful way to think about acids and bases is that after they've donated an H plus, if they're an acid, or accepted an H plus if they're a base, they've kind of almost turned into the opposite type of compound. So when OH minus accepts an H plus, there is some possibility it could reverse this reaction and reform this. Now, in this example, it really doesn't happen, but we still maintain this kind of idea. And we call these, when you have a base and then the acid formed as an H plus is added, that's called a conjugate pair. And over here, we have an acid. When it loses its H plus, it becomes something called a conjugate. It's called a sort of like a base. Now, for this example, HNO3 is a strong acid. OH minus is a strong base. So these essentially, they turn completely over into these compounds, and they really don't go back. The equilibrium does not lie very much at all on the reactant side here. But we can still use this conjugate acid-base pair idea. So everything that acts as an acid or base, it forms a conjugate that is the opposite. Down here is another example where we have a base, ammonia, and we have water acts as an acid, and we can form a conjugate acid of the base. This is called ammonium, and a conjugate base, hydroxide. These are, that's all I want to tell you, that these acid-base conjugate pairs form, or that's one way we can think about acid-base reactions. So we're specifically going to be using indicators, and indicators are weak acids or bases that have a different color in their acid and base form. And if we think about an acid indicator, we're going to call HIN. So the IN there just means indicator, not like indium or something. But so if we have the indicator, it reacts with water and forms its conjugate base. And this could just as easily work for a colored base that gains an H plus and forms a conjugate acid. But we're thinking about an acid indicator. So the equilibrium constant for this is an acid dissociation constant, and it's written over here. And we can see that the Ka, this is going to be a constant, as long as temperature is constant. And we have the concentration indicator, concentration of H3O plus, and in the bottom we have the concentration of HIN. Now, the indicator is going to be present in very small amounts, and so really the indicator itself doesn't have a large effect on the H3O plus, the hydronium concentration. That's going to be affected by other solution or other compounds in the solution that we're trying to figure out the pH of. So what we want to think of is that when we're using an indicator, the H3O plus is kind of being almost exclusively determined by another compound. And as a result, what happens is the ratio of the base form and the acid form of the indicator, they change so that Ka is maintained. So Ka is a constant. If we set H3O plus, and then these two concentrations are interrelated, because once, when HIN disappears, it forms IN minus, or when IN minus disappears, it forms HIN. So these are not independent of each other. And as a result, if the hydronium ion concentration is determined by an outside source, this has to change in order for Ka to keep to be present. Now, there's a slightly different way that we can talk about this. Ka values are usually really small values, like 10 to the minus 4 or 10 minus 8. It's just a little bit hard to discuss these really tiny numbers. So often we talk about the pKa. And the pKa is, if you remember, it's similar to pH. To get pKa, you take the minus log of the Ka. And we can do that over here. So if we take the minus log of Ka, we get this, and that's the pKa. But if we take the minus log of this side of the equation, we've got to do the same over here. And now we're going to look and see that there are some odd properties of logarithms. And one of them is that the log of A times B is equal to the log of A plus the log of B. So when we take the negative log of indium, or IN minus, the indicator base and the indicator acid concentrations and the hydronium, we can separate that into, we're going to just selectively factor out or take out the hydronium ion concentration and put it by itself. And then we're going to have minus log of the base in the acid form. And we do that because this thing right here, that's the pH. And so we're going to substitute pH there. And this is the pKa, so we got there. Now, the other weird property of logarithms we're going to use is that the log of A over B is equal to minus the log of B over A. So if we take these two quantities and flip it, that changes the sign. It becomes the opposite sign. And so that's how we get this thing. And this is a form. It's kind of related to, it's not exactly the form, but this is related to something called the Henderson-Hasselbach equation. And what this kind of tells us is that, all right, pKa is a constant. It doesn't change. pH does change depending on what's in the solution that we're measuring. And in order for pKa to be constant, the ratio of the acid form and the base form for the indicator has to change. And so that's how the indicator is going to tell us about pH, because it has to change in order to maintain this. And as we change these two things, we change the color. So what can an indicator tell us? Well, basically what it tells us is that whether there's sort of three possibilities. One, we're about 1 pH unit above the pKa, then we just see the base, or we almost exclusively see the base form. We're 1 pH unit below the pKa, then we'll see almost exclusively the acid form. And then when we're kind of within that 1 pH unit of the pKa, then we'll see a mixture of colors. And you can sort of see that up here with bromocreosol green. Its pKa is 4.7. And the difference between these two is just that up here, there's 1 drop of indicator, here it's 2 drops, so you get a little bit more intense colors. But you can see that at acid pHs, at 3.5, you get yellow. At more basic pHs, you get blue. And in between, you get green, because green's a combination of blue and yellow. So if we're using bromocreosol green, we can say we are like below 4 maybe if we're yellow, and we're above 5 something if we're blue, and if we're between, if it's green, it's sort of between 4 and 5 somewhere. There are some, I just include this one because there are some indicators that have more that have more than 2 colors. Thymol blue actually has 3 colors, and it's a diacid, means it has 2 acidic groups. And so you can think of the acidic form, that's the fully protonated form, or where you haven't lost any H pluses, is red. And then when you lose 1 H plus, it gets to be yellow. And when you lose 2 H pluses, it gets to be blue. And so you can, this is a little bit different, but it allows you can tell either whether you're you're down here, you're in this area, or whether you're up here, depending on the color. So this is a figure that I found in online, and it happens to include all the dyes that we're interested in, and or that are used in this experiment. And you can see that each of them each of them has different pKa's, and thymol blue actually has 2 pKa's, like we saw in the last slide. And you can see this is thymol blue, and it should say step 1. They missed the 1. And then over here is thymol blue step 2. So this is, if you're looking at yellow and red or orange, you're sort of around the first pK of 1.6. And if you're seeing yellow or blue or maybe a little bit green or sort of in between, then you're sort of around the other pK of 8.9. But the idea is that you look at all the colors and they sort of, it points you to what the actual, or an estimate of the pH. So, if you're yellow, then you know that you have to be sort of above about, if thymol blue is yellow, then you're above, maybe 2.6 or so. You're up in here. But then if you're blue, then oh yeah, now I know I'm above, like with bromophenol blue, now I'm sort of above maybe 4.5. And then you just keep going until you find sort of where one you're in the base form, another you're in the acid form. You say, oh, I have to be kind of in that area. So by looking at by looking at a series of indicators, you can narrow down what the pH of the sample is. One question that sometimes I always have is, or I thought when I was learning this stuff, is we want to determine the pH of our solution, but we're adding a weak acid or a weak base, the indicator, to it. Does that change the pH of the solution? And it turns out it doesn't. And the real reason is because the indicators are at very low concentration. And over here I got some data that hopefully supports that. So if you look in a book about how to make up these indicators, I didn't find I didn't find, but I got 6 out of them. Here you got concentration. Usually they're made as solutions in mole volume percent. So it says like dissolve. For this first one, it might say dissolve 0.0 or excuse me. It'd say dissolve like 0.04 grams in 100 milliliters, and then that's your solution. And sometimes, actually, and lots of times the solvent isn't water. A lot of times it's something else, because these compounds may not be really water soluble. But if you take that mole volume percent and you convert it into a molarity, you can see that the molarities here are very small. And the solutions you're testing in this experiment are all 0.1 molar solutions. And so, this is 2 times 10 minus 3. That is actually 50 times lower in concentration, and that's the highest of these. And you can see a number of these are even smaller. So 3 times 10 minus 4 will be almost 500 times less concentrated. So the concentrations of the indicators are just really low. We also have to factor in dilution. So for this experiment, it's not so much because you take like 2 or 3 milliliters or 2 or 3 drops of the solution being tested and 1 or 2 drops of the indicator. So you're diluting both of them by about half, because you're adding about equal amounts of each. But a lot of times you'll be putting 2 or 3 drops of an indicator in like 10 milliliters or 20 milliliters. A drop's about 20 microliters. So there's a huge 20 microliters is a 50th of a milliliter. So 1 drop in 10 milliliters is about 1/500th dilution, and so lots of times these concentrations are very low. One of the solutions tested in this experiment is a 0.1 molar aluminum sulfate solution, and you should see that its pH is acidic, and there's often a lot of confusion about why that happens. The sulfate does not significantly affect the pH. It's the aluminum that is affecting the pH, and this happens with not all metal ions, but a few, including aluminum and iron, aluminum 3 plus, and iron 3 plus. And what happens is they form a complex, often a hexahydrate complex. And so there's just 6 waters around the iron, and this is a complex, and the charge is spread out over the entire complex of iron and water molecules. This thing can act a little bit like an acid because it will set up an equilibrium with water where one of the waters of the complex can donate its H plus to the water, and so you get this thing. So an H plus has been donated, so overall charge changes from 3 plus to 2 plus, and now we have 5 waters and 1 OH, and then we've formed hydronium. So aluminum 3 and copper 2 also undergo this process. They both form hexahydrate complexes that are acidic. So in summary, indicators are weak acids or bases that change color as the protonation state changes, as we either add or subtract an H plus. One indicator, it doesn't, it has a limited amount of information. It tells you whether you're, 1 pH unit or more above or below the pKa, or if you're around the pKa. And that's enough for a lot of situations. Like in titrations, all you got to know is, have I reached a certain pH? And so if you choose your indicator right, it'll tell you when you've transitioned from below the pKa to above the pKa, and if the pKa is in the right spot, that's all you need to know. But if you're trying to estimate the pH of a variety of compounds, you need to use, with a variety of pHs, you need to use a series of indicators, and that's what's going on in this experiment. Good luck. I hope you enjoyed doing or making observations.